is equal to 0. Okay. So later on, I'll tell you why is that. Okay. So what we are going to do in the next step. So the first step is we remove the support. The next step that we're going to do is we are going to put back, or we're going to put a redundant load at point B. Okay. So this is our structure. So when you put a redundant load, the redundant load will push the structure back to its original position. Okay. It will push it back. Okay. So again, I'm going to label this is our point A, point D, point C, point K, and this is our point B, right? So we are going to put a redundant load, and this redundant load, I'm going to call it RB. Okay. So this is our RB. At point B, and this is our redundant load. And the purpose, what is the purpose of the redundant load? Okay. The purpose of the redundant load is such that when you allow the structure to extend, this redundant load will push it back. Okay. So this is our delta R. Okay. So as you can see, the deflection due to the applied load and the deflection due to the redundant load are not in the same direction, like what we have written earlier. Okay, and finally, this green line that you have seen down here, okay, mathematically, what it's trying to express over here is such that the deflection due to the applied load plus by the deflection due to the redundant load must be equal to what? 0. Because in reality, right, if you look at the extreme left diagram, you have a support down here. And it's impossible for the structure to pass through that support. But based on analysis, we allowed it to extend and we allowed it to push back. Okay. So some of you will say, Eugene, what is the purpose of such application, right? It's basically this type of analysis is great when you are calculating the load or the distributed load of a floor. Okay, how much load can you how much force is applying on the floor to support a piano, for example, where the floor is deflecting. Okay, then you have to estimate how much you have to push back. Then at below, you have to build a foundation to strengthen your piano, for example. Not ordinary piano, a grand piano. Okay, I hope you realize that you cannot just put a grand piano anywhere. Okay, that thing is heavy. Okay, the weight approximation, yeah, is about maybe like 350, 400, depending on the size of the piano. Some piano weigh as much as 500 kilograms. Okay, really, really expensive one. The price of, yeah, I've seen a grand piano selling for $350,000. Ridiculous. Anyway, right. So this is what we're going to do now. Okay, we're going to put in terms of math. Okay, I'm going to do the same thing. Okay, we're going to calculate this structure. We're going to remove the support and then going to add it back. Now, one thing I want you all to look in this diagram over here. Okay, that's where a lot of students make mistake. Okay, so when you add the redundant load for your analysis, okay, do not consider the applied load. Okay, Why? Because when we on the left hand side, or on the one I'm circle in blue now, we already consider the applied load. Okay, the one I highlight in yellow, you just need to consider the redundant load. Okay, so just to forward how our steps look like. On the left hand side, where we remove the support, okay, we have to divide the structure or divide the analysis into 4 sections, right? Why? Due to the applied load and due to the change in what? Geometry. Yes or no? Due to the, so we have to section this in this region over here. This is our section 1, section 2, and then this is our section 3, and this is our section 4. Okay. Well, on the structure on the right, question for you: how many sections do we need to divide to? 1, 2, 3, or 4? Anyone?
1.
It cannot be 1, 2. Okay, you are right. Okay, so why 2? Because both of them CRB, but the change in geometry is only at point C. So we have to look at 1 and 2. Okay, so be very cautious about this. Well done. Okay, so a lot of you can visualize what is going on already. Okay, so this is how we are going to divide our structure when we remove the support, and then we push back. Okay, we only need to divide by 2. Okay, because what? We do not need to consider the applied load when we add the redundant load. Okay, okay, so let's do the analysis now. Okay, so we are going to do step 1, or remove the support at point B. Okay, we're going to remove the support at point B. So let me go down further. Oh, before I go down, have you all finished copying everything down here? Yeah, I'll give you some time to write if you need to write things down. Or anyone, any questions so far? Okay, I hear nothing and I don't see anything on the chat. Right. Yes.
Sorry, do you mind just re-explaining why what's it called, like the first step is divided into 4 parts and the second step is divided into 2?
Okay. Ok para. First of all, do not call me sir or do not call me Professor Ng. Okay, just call me Eugene. Are we clear? Okay. Now
Yeah.
I will explain. Why is because the reason how we divide them into parts is dependent on 3 things. 1 is the applied load. 2 is the change of geometry. 3, is there any change in material? Okay. So for this part, change in material, they are all made of the same material. Okay, there's no like A to C is one material, C to B, no. They're all made of the same material. Okay. If we just look at the change in geometry, right? So if we change geometry, AC and CB is just only 2 change in geometry. Okay. Now we look into the change in the applied load. Okay. Or where the applied load is applied. So from A to D, you will see the 300, 600. Yes or no? Right?
Yes.
At 2, right? You only see 600. You don't see the what? 300. So there's a change in what? Applied load already. Okay. At 3, right? You only see the 600. Same like 2. Right? I think this is I think speaking did not really help. I will write this down. Okay. So at 1, right? The load is 300 and 600. Okay, so that's why you have to. So now you'll say, how about 2? At 2, the load is only what? 300. It's only 600. Right? So the load is not the same. You have to divide already. Right? At 3, the load is 600, but geometry change. What do you mean by geometry change? Section 2 and 3, they don't have the same geometry. Yes or no? Right? So you have to divide it. Right? Then at 4, the load is 0. That's why you have to divide it again. Okay, so that's why altogether 1, 2, 3, 4. Okpara, is that okay for you?
Yeah, that makes sense. Thanks.
Okay, that is why we divide it. Okay, so again, we do not need to use the part where there's a change in material. Okay, everything's made of the same material. Right. Then we go over here. So we are going to calculate deflection. So now we're going to remove the support at point B. So I'm going to like I can't crop this diagram. So we removed here. Okay, so this is the one that's removed. Okay, so we are going to do calculate the total deflection induced by the applied load. And the formula we're going to use is deflection is equal to PL over AE. Okay, and we know positive is tensile, negative is compression. Okay, we know that. Okay, so now we calculate deflection, and so we're going to divide this into section 1, section 2, section 3, and section 4. Okay, so this is in fact very similar to your homework. To your quiz. Okay, so all of you will probably know this very well. So deflection of 1. So 1 was see the what, the 300 and the 600. Okay, so 300. I'm using the hangman theory again. Okay, plus by 600 times 10 to the power 3. Length is 0.15. Cross-sectional area is equal to 250 times 10 to the power minus 6. Young's modulus value was not given. We just put it as E. Okay, so this will be equal to 900 power 3 times by 0.15 divided by 250 power minus 6 is equal to 540 times 10 to the power 6 positive. Divided by E. Okay, then deflection of 2. So 2 will not see the 300, right? Because it's above it. Okay, and you only see the 600. The length is again 0.15. And then divide by the cross-sectional area. And then E. So this is equal to 600 power 3 times 0.15 divided by 250 power minus 6. So it's 360 positive. 360 times 10 to the power 6 divided by E. Now, some of you might have issue with converting from millimeter squared to meter squared. I'll do this. Okay, I'll do some side work because the rest are very repetitive. So from 250 millimeter squared. Okay.